So thank you, Ludwig, and hi everyone. I'm Tianzhu Zhang. I'm a new member at Nokia Bell Labs, and I also just became associate member of Links. Today, I would like to present our ongoing work about performance benchmarking of the state-of-the-art software switches in the context of network function virtualization. Before I start, I would like to introduce myself. I got my PhD from Polytechnic University of Turin, and after that I came to France. I started as an intern at Nokia Bell Labs like 3 years ago. And after that, after the 3 months internship, I became a postdoc researcher at Telecom Architect. My supervisors were first Professor Dario Rossi and then Luigi Iannone. And after that, I joined Nokia Bell Labs after 8 months of unemployment. Finally, I got the permission from the prefecture to join. And then let me talk about this project. This is a joint work between Telecom Paris, Nokia Bell Labs, and Polytechnic University of Turin. I would like to extend my gratitude to my collaborators, in particular Leonardo. He was a postdoc researcher when we started this project, but now he's an associate professor at Telecom Paris, but he still looks younger than me. And we have Massimo, who worked with me for 3 years. He was affiliated with Nokia Bell Labs during the beginning of the project, and then he left for Huawei. And then we have like Jim and Luigi. I think all of you know them very well. And we have Paolo from Politecnico di Torino. He was my PhD supervisor. I mean, except Paolo, all the rest of the collaborators are members or former members of Links. That's why I would like to present this work in this occasion, because I think this is really relevant. Regarding the results, we have already published some. We had a demo at NetSoft. Then we had a full paper at Connext. We still have ongoing works trying to extend it. So that's all. And then this is the outline of today's presentation. I will begin with the background to give you a little bit of context about network function virtualization software switches and also the motivation of our work. And then I discuss a little bit about the methodology, including the test scenarios that we defined for the software switches and also the testbed configurations. And if we have enough time, I will present some of the experimental results before drawing conclusion. So first, let's begin with the background information. The story all begins with the problem of the traditional networks, because traditional networks rely on specialized hardware appliances, namely middle boxes for service provisioning. Those middle boxes are usually very expensive to acquire and also require domain-specific knowledge with different vendors to manage. And those middle boxes are intrinsically inflexible to customize the given functionalities. Also, they are tightly coupled with the hardware product. Imagine that if we would like a new feature introduced to the devices, it might take years. So this really slows down the process of network innovation as well as the time to market. And in terms of service deployment and maintenance. Middle boxes also make the process tedious as the technicians have to go to specific sites to install the specific devices manually. They also need to guarantee the particular order of the different devices to fulfill the intended services. And these middle boxes are also not so easy because they are like monolithic, designed monolithically, and they are not so flexible to be scaled in and out based on the dynamic traffic load and also the other environment dynamics. So network function virtualization is proposed to tackle these issues. NFV, basically, the idea is to replace the, to replace the specialized hardware middle boxes with software-based virtual network functions, or VNFs we call it. Those VNFs can be deployed on commodity off-the-shelf hardware like the servers in our lab. The basic the fundamental contribution of NFV is the separation of the evolution timelines between the software-based network functions and the underlying hardware infrastructure. NFV can also cost effectiveness by consolidating multiple instances of network functions on high volume yet less expensive servers. And in terms of service provisioning, it can also become easier as NFV allows for optimally automated and flexible the service provisioning can also be like optimally automated and flexibly managed through software control mechanisms or APIs. And in terms of network function development, it is also just cut down to writing software programs using standard API. So with all these advantages, NFV remarkably promotes the network innovation and accelerates the process of time to market. Then a little bit background about software switches. As the name suggests, software switches are basically virtual switches implemented using software and intended to function the same as hardware switches. They are more flexible compared to hardware switches because of the software nature, but when it to performance, it usually falls short, and sometimes the performance gap between software switches and the hardware switches are really huge. Due to the performance disadvantages, software switches are usually in the past, most used for fast prototyping and functional testing. They are rarely used in production. But recent years, the story has changed with the emergence of high-speed packet I/O frameworks like Intel DPDK, NetMap, eBPF, and so on. These techniques can basically accelerate the performance of software switches by 1 or 2 orders of magnitude. Some software switches, when combined with these frameworks, can process packets at like 40 gigabit per second or 100 gigabit per second. Due to these reasons, software switches are now widely adopted by existing NFV frameworks for traffic steering between the network functions, also with the outside world. Although software switches are gaining popularity, there is still a lack of understanding of their respective performance. especially in the context of network function virtualization. This is mainly due to several reasons. First, as shown in the table, software switches are intrinsically different. They are designed with different architectures, processing paradigms, execution models, virtual interfaces, and they have different level of runtime reconfigurability. And although like many NFV frameworks have adopted some software switches, these software switches do have their primary design purposes. And also the performance of those software switches sometimes highly depend on the input traffic patterns, and also depend on the low-level parameters, like the hardware ones, or it can be hardware parameters or some software parameters. And in terms of existing works, there are indeed some prior work that focus on performance benchmarking of software switches. Here we show our taxonomy of prior works. Basically, they test different switches. Those switches spanning from high-speed domain to low-speed domain. We highlight in bold fonts the software switches that can operate at multi-gigabit per second. And then they also, this existing work, also tackle different other aspects, including the test environment, including the test scenarios, like these two columns shown, and also the different, they focus on different performance metrics. Some of them focus on bare metal test of the forwarding efficiency of different software switches. Some others additionally consider virtual environment, and most of them consider virtual machines as it was the standard, as they are the standard ways of virtualization. But recent years, containers begin to draw attention. And in terms of test scenarios, some of the existing work only focus on the inter-VNF communication, and some others focus on the service function chains. This concept I will introduce later in the slides. And then in terms of parameters, some of them only test the throughput, some also test the latency. In particular for throughput, all of them only measure the unidirectional throughput. They don't measure the bidirectional throughput. And based on our conversation with the Cisco network engineers, they believe that bidirectional throughput actually are more important and relevant, also more coherent with the real-world scenarios. So we would also like to consider this. The main problem of this prior work is that each of them only focused on a facet of the problem in their particular settings. And there is a lack of unified understanding of this performance benchmarking test. So here is our contribution. In this work, we would like to propose an experimental methodology to thoroughly evaluate the performance of software switches in the context of NFV. In particular, we use the methodology to compare the performance of 7 state-of-the-art high-speed software switches. We first analyze them based on quantitative results, and then we perform qualitative analysis. And the goal is not the goal actually for our work is not to find the performance of each individual software switch in absolute terms, because their performance vary with different test bed, with different versions of the underlying software, hardware tools, and also their performance can change with the kernel or OS upgrades. And then we also like to define the best use cases for each software switch based on our results. Okay, so now let's focus on the methodology. Because in NFV settings, network services are mostly provisioned in the form of service function chains, SFC. And consider in this graph a typical scenario in which part of a service function chain is deployed on a single server. And the service function chain flows like the arrow of network traffic indicates. And in this setting, we have like this server has two physical interfaces, and we have deployed 4 virtual network functions inside the server, and each of them has 2 virtual interfaces to communicate with the outside world. In a setting like this, if we would like to develop a detailed understanding of the performance of software switches for like in the context of service function chains, our observation is we would like to dissect the service chain into several critical hops. In particular, we have this hop, which is between the physical interface to the virtual interface. And these 3 identical hops that are between the virtual interfaces. And last but not least, the hop for the virtual interface to the physical interface. I think with this dissected way of analysis, we can develop a better understanding of the performance of each software switch, and also to identify the different bottlenecks under different settings. And then, based on the previous observation, we define the test scenarios. We define 4 of them. The first one is P2P. It's like the physical to physical. In this case, we have the SUT is the software switch under test, and we deploy each software switch here to forward traffic between 2 physical interfaces like this. The P2P scenario, we would like to include it because it provides a baseline reference to evaluate the overhead imposed by network functions running in virtualized environment. And then we have the P2V scenario, which means physical to virtual. This can be mapped to the first hop of a service function chain inside the server, as shown in the previous slide. In particular, currently the direction is like this. We would also consider the reverse direction, like from VNF to the outside world, which can be mapped to the last hop of the service function chain. And then the third scenario, we have the virtual to virtual. This is used to assess the traffic forwarding efficiency between like a consecutive virtual network functions inside the server of a service chain. And then we have the loopback scenario, which combines the observations of the previous 3 scenarios. Here we only draw like one virtual network function here, but actually we can have a chain of 1 to 5 VNFs like this, and the software switches just forward the packet sequentially to all those VNFs and then forward it back to the other physical interface. And based on these test scenarios, we select 7 state-of-the-art software switches to test their performance. They include.
Sorry, maybe.
Yeah, please.
Slide.
Yeah.
If you don't mind. In the loopback,
yeah.
Do you suppose that the packets are treated on the flight, or it may be that a request arrived to a VNF and the VNF will create a completely new flow?
We didn't consider this case, and yeah, because we only consider like the packet arrived here, and then it is forwarded to the VNF and then forward back. But because we focus, what we would like to do is to like understand the baseline performance of these software switches. And also consider that if we like inject the packet at the maximal rate here, and in this case, if the traffic load is like if the traffic load is very high, either this one or this one is bottlenecked, and in that case, our scenario can cover that case.
I understand. If this is the case, maybe you would like to have a fifth case, case number E, where the VNF is generating the traffic towards the rest of the world. Because the performance of your server doesn't need to be symmetric. So if you compare with P2V, maybe you would like to have a V2P.
Yeah, exactly. Actually, as I mentioned before, we also considered the reversed direction, but we didn't consider it like in this setting.
Okay, I got it.
Yeah.
Okay, thank you.
Yeah. Okay. So we select 7 state-of-the-art software switches, including OS DPDK. This is the industrial standard software switch. Then we have fast click developed by people in Belgium. They are like a modular switch, can process packet at a very high speed. And then we have the BES switch by UC Berkeley and the VPP from Cisco Systems. Then we have this P4S. It's a P4 software switch. It can support all the P4 semantics. We find it in a SICOM paper. And then we have the Snap switch, which is a flexible programmable software switch that can also run at high speed. And then we have the Valet switch. It's based on the NetMap API developed by people from University of Pisa. We select all these switches because they are open source. And they like are widely used in the NFV community. And also they can run at very high speed, even with relatively small packets. Then we have the software tools. These are like maybe too detailed, so I won't like explain. I won't like introduce them one by one. We have like different traffic generators and monitors that can help us build the different test scenarios. And then since the focus of this work is on network function virtualization, we do consider different hypervisors to build different virtual environments. For example, we use QEMU to build CentOS 7 based virtual machines. We also use the Docker and you use the Docker tools to build Docker images that can run network functions at high speed. And then in terms of these virtual network functions, it can be traffic generator and traffic monitors if it's for the P2V and the V. And for the Loopback case, we use layer 2 forwarding applications like test PMD and Valet forwarding. The main challenge of this work is to configure and how to like configure the large set of tools, different tools to implement the. And here is the detailed configuration of the previously described logical test scenarios. In our settings, we have like a single server and running on 2 NUMA nodes to emulate 2 servers. You can ignore the the detail about NUMA node, you can just consider that each of the NUMA node here act like an independent server. And then each server has like 2 physical ports that can run at 10 gigabit per second, and each pair of the port is directly cabled through using an Ethernet cable. And in the P2P scenario, we use Moongen here, and we deploy the software switch on the other server. And then the Moongen can inject traffic through one port and go to the other port of the other server, and then forward it back through the other pair of through the other pair of ports. And then here we have the P2V scenario. Compared to the P2P scenario, we add the virtualized network functions here. And this arrow here is for unidirectional test. We use FlowWatcher DPDK as traffic monitors. And then we also have bidirectional test indicated by this arrow. In this case, we have packetgen DPDK and packetgen as both traffic generator and traffic monitor. And then we have the V2V scenario. In this case, different from the other scenarios, we only have one server because we would like to measure the VNF traffic exchange inside a single server. And then the loopback scenario, as described before, we want to test the performance of software switches when it forwards traffic for service function chains with different lengths. And note that inside here, as mentioned before, we only configure layer 2 forwarding, because it's the most simple virtual network function. It imposes minimal computation workload, so that it will not bias the performance of the software switches. And then we have like some fundamental experimental parameters. In particular, we have the traffic patterns. We generate the traffic pattern is like we generate synthesized identical packets, and we only change the packet size in different experiments. We actually were thinking about including more complex traffic patterns in the future extension of this work. And then we have the CPU assignment. We particularly reserve CPU cores for both the software switches and for the virtual network functions. We note that we assign 4 cores to each of the VNFs so that they do not become the performance bottleneck during the test. For the virtual environment, we consider both VM and container as described before. And in terms of the performance, we test both the throughput and the latency. The throughput is tested both in unidirection and in bidirection. And for latency test, we measure the round trip time by injecting specifically, injecting specially time-stamped packets, and then measure their round trip time. And they're like 10%, 50%, and 99% of the maximal forwarding rate of each individual software switch, so that we would like to see their processing latency and their high, medium, and low input load. And okay, and then I would like to discuss a little bit about the experimental results. And here is the test for throughput test for P2P scenario. We include the test PMD. Here is a DPDK application configured to simply forward all the packets as they are. It is used as the baseline here to analyze the performance of other switches. And we have unidirectional traffic with different packet size, and then in this figure in the right, we have the bidirectional traffic, and then we have the throughput measured here. And based on this figure, we can say in general that with packet size like more than 256 bytes, all the software switches can reach 10 gigabit per second processing rate with unidirectional traffic. And the interesting case is this, where we have like a small packet size, which also means the most this also means the most stressful scenario. And in this case, you can see like actually the BAS, fast click, and VPP, they have like identical performance with the test PMD, and they reach the 10 gigabit per second. And this is also the rate of the network card. So they are really efficient. But other software switches like Snap and OVA, Snap failed to do that because it has some overhead imposed by its internal intermediate buffers. OVS DPDK also failed to saturate the 10 gigabit per second link, and the same as T4P4S, because these two switches, they have extra overhead imposed by their internal mesh and action pipelines. And then we have the wireless switch, who performed the worst due to the packet copy operation between the physical ports, between its two physical ports. And then this can be very expensive at a high-speed packet processing domain. Aside from unidirectional traffic, we also have like a bidirectional traffic that follows similar trend as the unidirectional one. And most of the software switches also can saturate in this case, it's 20 gigabit per second for bidirectional. And we also observe that BAS performs the same as the baseline test PMD, because both of them have very simple processing. And then remember, like fast click and VPP, they performed the same as BAS before, but in this case, they are outperformed by BAS. As we check their different implementation, we think that fast click failed to do that because it has like extra header extraction and update operations. And for VPP, it also performs a set of field verification operations. So that's why they are outperformed by BAS. And the other switches, they follow similar trend as the previous. And in particular, the Valet cannot even saturate the 20 gigabit per second link at 256 byte packets because of the packet copy operation that impose non-negligible overhead. After the P2P scenario, we also have like a P2V scenario, in which case we introduce virtual network functions. They can run inside the VMs like shown on the left side, and also they can run inside containers like shown on the right side. In general, the performance trend of these software switches in P2V scenario are the same as in the P2P scenario, but they also perform a little worse than the P2P scenario, because we compared to P2P scenario, we only like substitute one physical interface with a virtual interface, and this virtual interface and also its packet exchange between the VNF and the software switch actually impose a little more overhead than the same operation on physical interface. Then I would like to show, I skip the results for V2V scenario as they are similar. And then these are the throughput tests for the loopback scenario. And the trend is also the same. We have like both the unidirectional test and the bidirectional test. We have the VNFs running in VM in the first 6 cases, and then in the rest of the 6 cases, we have them running inside the container. For both virtual machines and containers, they basically present like a similar performance. And also as the service chain length goes longer, their throughput begin to drop as expected. And they drop because of different reasons. I wouldn't like go into too much of the details, or it will take too much time. And then I present a little bit about the latency test for the P2P scenario. Remember the latency test, we inject packets at 3 different rates, 99%, 50%, and 10%. Here on the x-axis, here we show the packet, the latency that of the specially time-stamped packets. I mean the latency in terms of their round trip time. And here we have the CDF of this round trip time. And we can see in general, as like the input traffic load decreases, these packets and these software switches usually impose less processing latency for each for the packets. There is like one exception is with this Valet switch, because it's based on NetMap API, and the NetMap API is like it's a mix of pooling and interrupt based processing. So when the workload is very high, it works on pooling, but when the input load is low, it switches to interrupt. And so that the interrupt also impose extra processing overhead. So in general, it doesn't change with a different input rate. Okay, and then I have the latency test for the loopback scenario, and yeah, I don't think I'm gonna discuss them because it will be very time consuming. But let's go to the summary of the use cases based on our all the experiments. I showed only part of them. I mean, all the experimental results can be found in our newest technical report. And based on our experimental results, we have several observations. First, there is no absolute winner that can outperform the others in all the different test scenarios with different virtualized environment with different input traffic patterns. And the second is the performance of software switches dealing with VNFs running in virtual machines and running in containers are very similar. And then for each of the switch, we would like to have summarize their best use cases and also have some remarks about them. In particular, for best switch, it achieves the best performance in all the container tests. So it's very suitable for doing the chaining for containerized network functions. And then we have the Snap. It is very convenient to use, and it's best for fast prototyping or also test different network functions, but it performs poorly with very long with service function chains in general. And then we have fast click, VPP, and Valet, who they all performed very well with service function chaining, but they do have different. They do have some other issues like fast click. Because it enforces strict batching, so it has very high latency when the input rate is very low. For Valet switch, it's tightly coupled with the NetMap API on the host, so it has like live migration difficulties. Also, it presents limited traffic classification capabilities compared to the other software switches. And then for OVS DPDK and T4P4S, they are less performant in the NFV settings compared to the others, but they do have other values. For example, OVS DPDK supports the SDN semantics, and T4P4S can integrate the P4 processing semantics. So these are also very valuable because in many cases people want to combine both SDN and NFV to implement more advanced management, service management, and orchestration schemes. Okay, so I draw the conclusion here. Software switches are widely used by NFV frameworks, but there is a lack of a benchmarking methodology to comprehensively understand their performance and identify their bottlenecks. And then we propose this evaluation of state-of-the-art high-speed software switches under the NFV setting, and we perform quantitative measurement, but we use qualitative evaluation. For the code and for the code, the script, they are reproducible. We have like these two badges issued by ACM Connects, the Artifact Evaluation Committee. Actually, we should have won the third badge if the reviewers had similar hardware, but they didn't have, so they only evaluated one test scenario. So they gave us this functional badge. It's also fine. And then the scripts and all the code are available on GitHub. So you are welcome to download them and test it on your own test bed or extend it. Okay, so thank you. And that's all from me.
So thanks, Tianzhu.
Hi.
Yeah. Any questions?
I've got a. So can you go back to slide 24?
24. Okay.
Yeah. So it's probably any question, but I don't understand.
This one?
No, the one before.
Okay.
Usually you use the quantile to give a view on some distribution. The one, not this one, the one with CDFs, the cumulative distribution function.
CDF?
Yeah, this one, exactly.
Yeah. Yeah.
So my question was, what are the, actually you've got two distributions there. One distribution from which you extract the quantiles, 0.01, 0.05, and one distribution from which you extract the CDF. So can you explain to me which is which?
Sorry, I mean all of them like are CDFs here.
But if you've got a CDF, the CDF also gives you all the quantiles. And here you have a CDF of quantile. So you have two.
No. Sorry, actually we have like a CDF of the individual round trip time. So like each point here, like so like it's like we have a set of specially time-stamped packets, and then we inject them inject them into the network, and then we get it back, and then we measure their sequence of like delays, and then we, based on those different delays, we plot this CDF.
Okay, but what's the 0.99 and the 0.50 for then?
The 0.99 is for like for the packet, for the specialized timestamped packets, we inject them like at fixed, intervals, and then the real environment actually is like at the same time we also inject other packets into the software switch, and these are for the injection rate of the other packets.
Okay. So it's the ratio between a monitored packet and ejected packet?
Yeah, it's like, yeah, exactly.
Okay, yeah, this is what I missed. Okay, thank you for the clarification.
Yeah.
Other questions? Well, I have one from my side. So what you did is you compare different software solutions for switching.
Yeah.
On a given hardware, I suppose.
Yeah. The same
so
setting.
My question is, if you change the hardware, so it may change the performances also.
Yeah.
And can we have, in this case, maybe some software that are better adapted to some hardware and less adapted to other ones? And so the comparison may change in that case.
The exact number I got here might change, because we did have this experience. If you check our original technical report, also the website for the NetSoft demo, and then if you check the current technical report, the values are not the same, because during this period we have like we have one kernel upgrade, and then we also have like multiple like change of software, because other people also visit our server and they also done something, and then the values are not the same, but the trend actually are the same. And they have
the trends are the same. Okay.
I have like three different sets of the whole run of all the experiments, and the trend didn't change. Yeah.
Okay, thanks.
Yeah.